So we have the map phi tilde from x tilde to Cm. We are going to define phi tilde from Sx tilde to Cm, which is an extension of phi tilde as follows. Let lambda from 0, 1 to Cm be such that lambda at 0 is M, lambda at 1 is the empty set, and sup area of boundary lambda t in 0, 1 is approximately equal to W. Then we define psi tilde x comma t is equal to phi tilde x intersection lambda t if t is in 0, 1, and this is equal to m minus phi tilde tx intersection lambda minus t if t is in minus 1, 0. So then one can show that psi tilde is a well-defined map on Sx tilde, and this is Z mod 2 equivariant. Moreover, psi tilde restricted to x tilde is the map phi tilde. Now, since psi tilde is Z mod 2 equivariant, psi tilde descends to a map psi from y to Zn, and we'll have psi restricted to x is equal to phi. Moreover, we also recall that phi from x to Zn is a k sweep out. These two facts, that psi restricted to x is phi and phi is a k sweep out, implies that psi from y to Zn is a k plus 1 sweep out. We'll need this fact later. So I'll draw another diagram here. So we have this boundary map from Cm to Zn, which is a double cover. And then we constructed a double cover x tilde of x. We started with this map phi from x to Zn, and phi tilde is a lift of phi. And then we constructed the suspension of x tilde, Sx tilde. So x tilde sits inside Sx tilde. And then we considered quotient of Sx tilde by Z mod 2. We call this space Y. X sits inside Y. Then we define psi tilde from Sx tilde to Cm. Psi tilde is Z mod 2 equivariant. Psi tilde is an extension of phi tilde. And then psi tilde descends to a map psi from Y to Zn, and this psi is an extension of phi. And this psi is a k plus 1 sweepout. So now we define x tilde, we define phi tilde to be the Sx tilde, comma x tilde, relative homotopy class of psi tilde. And then we construct a CCM hypersurface by applying the min-max theorem to this relative homotopy class phi tilde. But to apply the min-max theorem, we need to ensure that LC phi tilde is greater than sup AC phi tilde x, small x is in x tilde. Now to show this, we note the following. For x in x tilde, small x in x tilde, AC phi tilde x is equal to AC phi tilde x, because phi tilde restricted to x tilde is phi tilde, and this is equal to area boundary phi tilde x minus C times volume phi tilde x, and this is less than or equal to area of boundary phi tilde x. Therefore, sup x in x tilde AC phi tilde x is less than or equal to sup x in x tilde area boundary phi tilde x, but this sup is approximately equal to omega k by the choice of the map phi. So sup x in x tilde AC psi tilde x is approximately equal to omega k, and therefore it is enough to show that LC phi tilde is greater than omega k. So for this, we choose f tilde and pi tilde. Choose any f tilde and pi tilde, and then we note that AC f tilde y is equal to area boundary f tilde y minus C times volume f tilde y, and this is greater than or equal to area boundary f tilde y minus C times volume of M. Therefore, sup y in Sx tilde Se f tilde y is greater than or equal to sup y in Sx tilde area boundary f tilde y minus c times volume m, and this is greater than or equal to omega k plus 1 minus c times volume of m. So this last inequality, that is sup area boundary f tilde y is greater than or equal to omega k plus 1, follows from the following two facts. So the first fact is that there exists an Sx tilde comma x tilde relative homotopy between f tilde and psi tilde. So such a homotopy exists because f tilde is in the homotopy class phi tilde, the relative homotopy class phi tilde. And the second fact is that, which we already stated previously, that psi from y to zn is a k plus 1 sweep out. So using these two facts, we can prove this inequality. So for any f tilde and pi tilde, sup AC f tilde y is greater than or equal to this. Therefore, LC pi tilde is greater than or equal to this omega k plus 1 minus c times volume m. And our hypothesis is that this quantity is strictly bigger than omega k. So we have proved that LC pi tilde is greater than omega k. Therefore, we have proved this. Therefore, we have LC pi tilde is greater than sup AC psi tilde x. X is in capital X tilde. Therefore, the min-max theorem is applicable. So there exists omega such that boundary omega is CCMC and AC omega is LC pi tilde. And we already proved that LC pi tilde is greater than omega k. So in the statement of theorem 2, we had the existence of omega such that boundary omega is CCMC, and then we had an upper bound and a lower bound for AC omega. So we already have proved the lower bound for AC omega. AC omega is greater than omega k. And to prove the upper bound for AC omega, we prove an upper bound for LC pi tilde. So LC pi tilde will be less than or equal to sup AC psi tilde y. Y is in Sx tilde. This is because psi tilde is also an element of pi tilde. And now if we denote y as x comma t, then AC psi tilde x comma t is equal to area boundary psi tilde x comma t minus c times volume of psi tilde x comma t. This is less than or equal to area of boundary psi tilde x comma t. This is less than or equal to area boundary phi tilde x plus area boundary lambda t. So this follows from the definition of psi tilde. So I'm just going to write here psi tilde x comma t is equal to phi tilde x intersection lambda t. And now this is approximately less than or equal to omega k plus w by the choice of the maps phi and lambda. So we have AC psi tilde x comma t is less than or equal to omega k plus w. So therefore this quantity is approximately less than or equal to omega k plus w. This gives an upper bound for LC pi tilde, and LC pi tilde is equal to AC omega. So we have an upper bound for AC omega. So roughly this was the proof for theorem 2, and I'm going to stop here. Thank you very much.